Alright, in this video we're going to tackle both indeterminate products and indeterminate differences. Right? So there is only one indeterminate product, and that is 0 times infinity. Now infinity could be positive or negative, and this order could switch because of course this is commutative. But let's go ahead and look at the first example. So I have limit as x approaches infinity of x times tan of 1 over x. Alright, so you first wanted to make sure that this is an indeterminate product, because if it was infinity times infinity for some reason, the answer would simply be infinity, and we wouldn't need to do any work, right? Or if we had 0 times 0 for some reason, we would just get 0, okay? So we got to make sure we have an indeterminate product here. So if I let x go to infinity, obviously this first term is infinity. And so then if I let the x go to infinity here, okay, 1 over infinity, 1 over a really large number is 0, right? And tan of 0 is 0, right? We did that in the previous example. If you needed to see that, right, on the unit circle, 0 degrees is on the x-axis. The point on the unit circle is 1, 0. Tangent is sine over cosine, right? So tan of 0 is 0, right? So we do get this indeterminate product, right? Now, this is not L'Hopitalable, right? We cannot apply L'Hopital's rule here because L'Hopital's rule requires you to have a quotient, a function on top and a function on bottom. So what we're going to have to do to all of these products is we're going to have to change it to a quotient, right? So we got to write some forms of these two functions that are equivalent, right? So over on the side, I'm going to put x, okay, is equivalent to 1 over x to the negative 1. Right? Because if I move the x from the numerator to the denominator, I need to negate the power, right? Or if I move this up, I just get x, okay? So x is the same thing as 1 over x to the negative 1. I could make that substitution here, right? Or if I wanted to change tangent, tan of 1 over x. Tangent is the reciprocal of cotan, right? So I could do 1 over cotan of 1 over x, right? Because they're reciprocal functions of each other. Or 1 over tangent, right? And so you would flip the tangent up. Okay, but just know that tan and cotan are reciprocal. So I could make this substitution if I wanted to, right? And now it's not always easy to know which substitution to make. Sometimes you'll try one and it makes the derivative super complicated, or it makes the simplification super complicated, and so I would just write, abandon ship and move on to the next one, right? But I have some inside knowledge here of which function to use, and that is because 1 over x is really x to the negative 1 power. Right, so if I change this x to x to the negative 1 power, and I have an x to the negative 1 power on the inside here, things are going to start to simplify, right? So I'm going to choose to move the x to the denominator, right? Or change x to 1 over x to the negative 1. Let me go ahead and show that step. All right, this is the limit as x heads to infinity of 1 over x to the negative 1 times tan. We'll go ahead and change this x to the negative 1 as well, right? So I just made that substitution, right? And so now I can go ahead and multiply straight across and look at the limit as x goes to infinity of tan of x to the negative 1 over x to the negative 1, right? Now, is this indeterminate? It should be, but I want you to make sure. All right, so remember x to negative 1 is 1 over x. So if I let x go to infinity, 1 over x goes to 1 over infinity goes to 0. Tan of 0 is 0. Right? This is 1 over x again. If x goes to infinity, I get 1 over infinity, which is 0. Okay, so it is still indeterminate. And it should be, but I do want you to make sure you're verifying and making the correct substitutions, as well as being able to evaluate these determinate and indeterminate forms. So this is L'Hopitalable. Okay, this one is not, right? You can't L'Hopital a product. You have to change it to a quotient. Right? This one is L'Hopitalable. So I am going to take the derivative of the top over the derivative of the bottom. So on the top here, it's a chain rule, right? Because we have a tangent on the outside, x to negative 1 on the inside. So let me go ahead and outline the chain rule here. Get tan x on the outside, x to the negative 1 on the inside. The derivative of tangent is secant squared. The derivative of x to the negative 1 is negative 1 x to the negative 2, right? Because we bring the negative 1 out front and then subtract 1 from negative 1 to get negative 2, right? So now to finish off the chain rule, I need to plug b into a prime and then multiply times b prime. So I'm going to get secant squared of x to the negative 1, and then this is going to get multiplied times negative x to the negative 2. Alright, can't see that. I'm like on this edge of my paper there, but I got it in there. Okay, so then we want to take the derivative of the denominator, right? And this derivative is negative x to the negative 2. And this was how I knew I needed to choose, okay, to move the x instead of the tangent, right? And that's because this derivative would match the derivative of the inside function, right? So here, these are going to cancel, okay? Negative x to the negative 2 cancels on the top and the bottom. And so I just have the limit as x goes to infinity of secant squared of 1 over x. So let me rewrite that. The limit as x goes to infinity, secant squared of, I'm going to go ahead and change it back to 1 over x now, because I just need to evaluate that. Alright, so if x is headed to infinity, 1 over infinity is 0, so I need to know what secant squared of 0 is. Alright, so again, on the unit circle, if you wanted to go there, okay, what is secant of 0? Here's 0 degrees. Secant's the reciprocal of cosine, and so we're getting the reciprocal of 1, which is just 1. So this is 1. Right? So 0 times infinity is 1 in this case. Right? They both head to their respective value at a 1-to-1 ratio. Right? All right, so let's look at another indeterminate product here. Let's look at the limit as x goes to 0, cotan 2x times sine 6x. All right, which form is this? Okay, let me get my unit circle going here. We're looking as x approaches 0, right? So we're on the x-axis here. All right, what's cotan of 0? Cotan is cosine over sine, so I'm going to do 1 over 0. And 1 over 0 is infinity. Right? If the top is going to 1 and the bottom function's headed and getting super small, the fraction's getting big. All right. And then sine of 0 is 0. So we get infinity times 0 here. Right? So we have an indeterminate product, but we can't L'Hopital products. We can only L'Hopital quotients. So we can write cotan as the reciprocal of tangent, right? Cotan is 1 over tan. Or we could write sine as the reciprocal of cosecant, because sine is just 1 over cosecant, right? And so let me go ahead and write those down. Sine 6x is 1 over cosecant, right? Because sine and cosecant are reciprocals of each other, and cotan is the reciprocal of tangent, right? Usually you have tangent is the reciprocal of cotan, right? Well, no, this one's normal, right? And this one's normal. Sine is, or you usually have cosecant is 1 over sine. You're used to seeing this. But if I were to just flip both of those, right, then I get sine over 1 is 1 over cosecant. They're reciprocals of each other, okay? So it doesn't matter which one you choose, but one of them might be easier than another. I kind of I prefer the derivative of sine over the derivative of cosecant, and so I think I'm going to leave sine alone, and I'm going to change cotan, just for that simple reason, right? So I'm going to rewrite this and rewrite cotan as 1 over tan, right? So I'm going to leave the sine 6x up top and move cotan to the bottom as a tangent. So I get sine 6x over tan 2x, right? Is this indeterminate? It should be. Okay, this should be our indeterminate quotient here. Sine of 0 is 0, tan of 0 is 0, right? So this changed it to an indeterminate quotient. So I can L'Hopital this, right? Remember, you can't L'Hopital indeterminate products. You can only L'Hopital indeterminate quotients. So you have to change the forms. All right, so we're going to get the same limit here. Now the derivative of sine of 6x and the derivative of sine of 2x, they're both chain rules. All right, so let me go ahead and show the work. For sine x above here, the outside is sine x, the inside is 6x. The derivative of sine x is cosine x, the derivative of 6x is 6. So if I plug b into a prime times b prime, I'm going to get cosine of 6x times 6, or 6 cosine 6x. Right? Now I'm going to go ahead and do the chain rule for tangent. The outside is tan x, the inside is 2x, the derivative of tan x is secant squared, the derivative of 2x is 2, so I'm going to get secant squared of 2x times 2, or 2 secant squared of 2x. Alright, so is this indeterminate? If I go ahead and let x go to 0, 6 times 0 is 0. Cosine of 0 is 1, which means secant of 0 is also 1, right? Because they're reciprocals of each other. So I'm going to get 6 times 1 over 2 times 1, which is 3. Okay, so this indeterminate product here ended up being equal to 3, right? I believe that means that cotan goes to 0 3 times faster than sine, or something like that. Right? So let's go ahead and do one more product. I'd like to look at the limit, as x goes to negative infinity of x squared e to the x. Right? X is headed to negative infinity, right? So I like to evaluate these looking at the graph. I'd like to get the graph of x squared, and I like to get the graph of e to the x, right? So over here on the side, the graph of x squared is just a parabola, right? So if we were to look at the limit here as x heads to negative infinity, right? The function is heading off to infinity. So we're going to get infinity here for the first one. Now if I graph e to the x, right, it's an exponential function. You guys should be really used to seeing exponential graphs, right, with the COVID-19 going on right now. Okay, so we get this exponential function here. So now if we were to look, though, as x heads to negative infinity is on this edge, right? So as x heads to negative infinity, what is this exponential function doing? It's heading to 0, right? So I know the limit is 0. So we have infinity times 0, which is an indeterminate product. But we can't L'Hopital this, all right? We have to change it to an indeterminate quotient. We can move or write an altered form of x squared or e to the x, right? So x squared, I could change that to 1 over x to the negative 2. I hope you agree, right? Because if I just use my rules of exponents and bring this up, they're equivalent, right? Or I can do e to the x is equivalent to 1 over e to the negative x, right? Just using my rules of exponents there. Because if I wanted to bring this up, I would get e to the x. Right? Now, which one do you move? Right? This one here, it is tempting to move the wrong one, but it'll be really obvious on the second L'Hopital's rule that you move the wrong one. All right? So you got to pick. Would you like to do the derivative x squared and the derivative e to the negative x? Or would you like to do the derivative e to the negative x and x to the negative 2? All right? So let me go ahead and pick, I'm going to pick the wrong one for now, okay? I'm going to choose the x squared, okay? And I'm going to move the x squared down, and I want to show you why this is the wrong pick, all right? So I'm going to get e to the x on top. I chose not to move that one, and I chose x to the negative 2. And this is it's tempting because the derivative e to the x is so simple, right? The derivative e to the x is e to the x, right? But if we were to apply the L'Hopital's rule here, is it indeterminate, right? So again, we're going to let x go to negative infinity. So e to the negative infinity is 0, right? And this is 1 over x squared, right? 1 over x squared. And so if the x is going to negative infinity, I'm going to get 1 over infinity, which is 0. Okay, so we are going to get 0 over 0 here. All right, so it is L'Hopitalable, so I am going to go ahead and take the derivative. And the top function is going to stay the same, and the bottom function is going to be negative 2x to the negative 3, okay, which is still indeterminate, right? We're still going to get 0 over 0. And if I keep doing L'Hopital's rule, the top is never going to change, and the bottom function is just going to keep getting x to a negative 4, x to the negative 5, x to the negative 6, and it's never going to go away. All right, so this is like an infinite loop of L'Hopital's rule, and you'll never be finished with the problem. All right, so instead here, I'm going to write abandon ship, okay? Because upon analysis, this is not going to lead us to an answer ever. All right, so let's go ahead and pick and move the e down and keep the x squared above. All right, so we're going to get the limit as x goes to infinity, leave the x squared on top, and move the e down. All right, so this is e to the negative x in the denominator. So if this is indeterminate, we can use L'Hopital's rule. Okay, so limit of x squared is infinity. And then here, if I plug negative infinity in there, okay, I can do negative times negative infinity, which is infinity, right? And so what's the e function doing as x heads to infinity? E of infinity is infinity. So we get a indeterminate quotient of the other type, right? This one gave us 0 over 0. This one's going to give us infinity over infinity. So we can L'Hopital rule this. Now I want you to notice, when we leave x squared on top, we have a maximum of 2 L'Hopital rules. Because the first time we L'Hopital, we're going to get 2x. The second time we're going to get 2, which is a constant, which means we're always done, right? So this function is going to go down to a constant, whereas this one was just going to keep getting more negative, right? So that's your big hint there. All right. So if I take the derivative of the top, I'm going to get 2x, right? Now what is the derivative of e to the negative x, right? It's a chain rule, guys. I'm going to go ahead and slow down, right, and take this derivative, because the derivative e to the x is e to the x, but the derivative e to the negative x is not e to the negative x, right? So the outside function is e to the x, the inside function is negative x. So if I take the derivative of the outside, I'm going to get e to the x. If I take the derivative of the inside, I get negative 1, right? So now I'm going to plug b into a prime, and then multiply times b prime, which means I'm going to get negative e to the negative x, right? So did this help? Okay. If I go ahead and look at as x heads to negative infinity, what is this limit doing? Okay. Well, what does 2x look like? 2x is a linear function with slope 2, right? So if I'm looking as x heads to negative infinity, as x heads to negative infinity, this function is heading to negative infinity, right? What's this function doing? Right? So if I let x go to negative infinity, a negative infinity is infinity. What is negative e to the infinity? Right? So negative e at the infinity mark. Well, negative e is the I'm missing my word right now, right? It's the reflection. Okay, this is a vertical reflection, so we're going to get this here. And as x heads to infinity, where is this function headed? To negative infinity. Okay, so we're going to get negative infinity over negative infinity there, which is L'Hopitalable. Which means we can take the derivative of the top and the bottom again. Right? So the derivative of the top is 2. Here, we're going to get an outside function negative e to the x and an inside function negative x. Right? Because this is just a constant times e to the x. So the derivative of the outside is negative e to the x and the derivative of the inside is negative 1. So plug b into a prime times b prime. I'm going to get negative e to the negative x times the negative 1. So this just changes it to positive, right? So I get 2 over positive e to the negative x. Now, I have a constant here, so I know my answer is in this next step. So the limit of 2 is just 2. Now here, I have a positive e to the negative x. But if I plug negative infinity in here, I get a negative infinity, which is infinity. So positive e to the infinity is this graph, right? And e to the infinity is infinity. So I'm going to get 2 over infinity, which is determinate. If the top function heads to a constant and the bottom function heads to infinity, the answer is 0. Okay? Which means that these functions kind of head to negative infinity about the same rate. Okay. No, that's not what that means. It means, God darn it, it means that let's see, let's go back up here. For this to be 0, it means that this function is heading to negative infinity, or is heading to 0 a lot faster than this function is heading to infinity. Okay. All right, so let's do our indeterminate difference. So we have one indeterminate difference, and that is infinity minus infinity. All right, and I just have a few examples of this. This isn't real prevalent, but I would like to go over them. So we're going to do the limit as x goes to infinity of the square root of x squared minus plus 1 minus x. All right, so on this one, if I let x head to infinity, okay, the square root of infinity squared plus 1 is infinity. And then if I let x go to infinity, I get infinity minus infinity. Right? You can't L'Hopital a difference either. The only thing you can L'Hopital is an indeterminate quotient. So I got to turn this into a fraction. And our standard technique here to change a two-term quantity into a fraction is to go ahead and multiply by the conjugate, right? So I'm going to multiply by the square root plus x, and then I'm going to pretend this is over 1, right? And I'm going to do the same thing to the bottom, multiply it by the same conjugate. Okay, this is going to do two things. It's going to help simplify the numerator, and it's going to create a fraction for us. Right? So if I were to multiply this out, okay, the square roots cancel. I'm left with x squared plus 1. The outer and the inner will cancel. X squared to x squared plus 1 minus x squared to x squared plus 1 cancel. And then last I get minus x squared. Right. And then on the bottom, 1 times the conjugate, I forgot my 1, is just the conjugate. All right. So here, let's go ahead and simplify this. Okay, let's not jump to L'Hopital's rule. The x squareds cancel. And so we're just left with 1 over the conjugate. And if we have a constant up top, we don't need L'Hopital's rule. This will be a determinate value. So if I let x go to infinity, I get infinity plus infinity on the bottom. 1 over infinity is 0. Right? So L'Hopital's rule not needed here. Right? But you can't always assume, the problem here, guys, is you can't always assume infinity minus infinity is always going to be 0. Because sometimes, right, the answer is infinity. Sometimes the answer is some other constant. So you have to be really careful here. All right, I have one more for you. For this indeterminate difference, let's look at the limit as x approaches pi over 2 on the negative side. Secant x minus tan x. All right, so on this one, I am going to look at the graphs here. Okay. Secant is the reciprocal of cosine, right? So the secant graph looks like this, right? Where it has asymptotes, right? It heads off to infinity here. So pi over 2 is right here. So if I look at the limit as x approaches pi over 2 on the negative side, it's looking at this part of the graph that's headed off to infinity, okay? So secant of pi over 2 on the negative side is indeed infinity. Right? What's tangent do? right? Tangent is these series of S curves, right, with asymptotes here. Tan of 0 is 0, then it heads off to infinity. So this is pi over 2 where this asymptote is. And so as x approaches pi over 2 on the negative side, okay, that's where this function is headed off to infinity. So we do get infinity minus infinity. Right, so this is an indeterminate difference. Now instead of doing a conjugate here, I'm going to write these in terms of sine and cosine and see what happens. Okay, I'm just going to change the form because I got to get it into a quotient if I ever want to use L'Hopital's rule. So I know secant is 1 over cosine. I know tangent is sine over cosine, so both of those are a quotient, and I just think it's a step in the right direction. So we're going to do the limit as x approaches pi over 2 from the left, 1 over cosine x minus sine over cosine it, right? So we have a common denominator, so we can go ahead and combine those. So I get 1 minus sine x on top and cosine x on the bottom, right? So now that I'm just dealing with sine and cosine, I am going to kind of use a unit circle here. Right, pi over 2 is at the top, and pi over 2 has the point 0, 1. So sine of pi over 2 is approaching 1. So I get 1 minus 1 up top. Cosine of pi over 2 is approaching 0. So I am going to get 0 over 0 here, right? So I can L'Hopital this. All right, so the derivative of 1 minus sine x is minus cosine x, right? Because the derivative of sine x is cosine. Apply the negative to it. The derivative of cosine is negative sine. Okay, so here we get cotan. And what is cotangent, right? Is that indeterminate or determinate, right? Or if we were to leave it as a fraction here and look at pi over 2, cosine is on the top, so we're going to get 0 over 1, which is 0, which should be the same thing we get for cotan. Yeah, let's go ahead and do that. All right. So if I evaluate this, okay, and plug pi over 2 in there, cosine of pi over 2 is 0. So I'm going to get negative 0 or 0. Sine of pi over 2 is 1, right? It's approaching 1. So I'm going to get negative 1 here. 0 or negative 1 is indeed 0. And cotan, the same thing, right? Because we get cosine over sine. Cotan of pi over 2 is 0 over 1 or 0. Okay. So this answer is 0 as well. So these examples, even though they're both 0, I want to caution you that the answer is not always 0, right? Sometimes it can be a finite number, so be aware, right? So indeterminate products and indeterminate differences have to be changed to a fraction before applying L'Hopital's rule, right? Keep that in mind. All right, the indeterminate powers to come on the next video.